The reaction that I chose to do for this chemistry project is the thermite reaction, which is a very cool reaction and actually has some real world uses. The main reaction for thermite is this right here. We start with powdered aluminum oxide or rust and aluminum powder. During the reaction, the oxygen switches partners and we get liquid iron because of the heat and liquid aluminum oxide. The main mechanism for this reaction is oxidation and reduction. The iron atoms initially have a charge of 3 and the aluminum atoms initially have a charge of 0. After the reaction, the aluminum has a charge of 3 and the iron has a charge of 0, meaning the aluminum gets oxidized and the iron gets reduced. The aluminum almost like tears the oxygen away from the iron and releases a lot of energy in the process. We can calculate that energy using the heat of formation and the heat of the reaction right here. I got these out of Google and checked them with the textbook, but the heat of formation of aluminum and iron are 0, so we kind of just don't really need those. The heat of formation of aluminum oxide is negative 1678, and the heat of formation of iron oxide is negative 825.5. So putting that into our equation over here, we end up with the aluminum oxide plus the iron oxide, and we end up with a delta H for the reaction of negative 850. That's a lot of energy. That's why we end up with liquid products at the end. The activation energy for this reaction is about 145 kilojoules per mole. It's pretty high, and we haven't learned this in class, so I don't know how to do it, but it's roughly 1200 to 1500 degrees Celsius for the reaction to start. Normally they add little bits of magnesium, which burns about that rate, or a sparkler, a big sparkler, and that gets the reaction to kick off. Professor Breakall helped me set up this reaction, so thank you to him for that. In our case, we didn't use magnesium or sparklers. We used a starting mix of potassium permanganate and glycerol, which will spontaneously ignite and set off our thermite mix. Okay, so this is a mix of aluminum and iron oxide. So currently there's not enough energy to activate it, even though it is spontaneous. We're going to put it in the sand, make a little divot spot for it. Make a little spot in here for our activating mix. That's good enough. Big enough for that? Yep, that's good. Cool. And then it's, you said potassium permanganate, right? Yes.
Okay. Okay. So now we'll go ahead and
We'll put the glycerin in to start the reaction, but I want to switch to slow motion real quick.
Okay.
Okay, I'll just quick fire.
Okay.
Go ahead when you're ready.
Okay.
I turned down the exposure for my phone because the reaction is super bright. So it looks a little dark right now, but you'll see in a second why I turned it down.
It should start within 15 to 60 seconds. So.
reaction happened. We're left with molten iron and aluminum oxide slag.
Great job, Ryan.
Yeah. Pretty cool, huh? Now here it is in real time. As it starts to burn, you'll see a blue-purple color in the flame. That is caused by the potassium inside of the potassium permanganate. Potassium starts to create its own really nice purple color if it's burned on its own. There are a few other elements that are commonly used in fireworks or party tricks to make other colors. For example, sodium creates a kind of a yellow color. As the potassium burns away, it transitions into an orange red with a little bit of white in there. The orange red is from the iron oxide or the iron burning off, and the white is from the aluminum. The sparks you see are from the molten aluminum and iron being flung out of the bucket by the reaction. Sometimes, if the reaction can get hot enough, it can get to the point where it will actually boil the aluminum and the iron inside of the container. I don't know if the reaction we had today was that hot, but if you want to see something like that, Veritasium has a few videos on Thermite you can go see. Here's the slag from the reaction. It has a little bit of sand on the bottom from the sand inside the can. But a lot of this is actually aluminum oxide slag that has solidified on the top. But inside there, if we could break it all open and get it out, is a little bit of iron right here that's settled at the bottom. The iron is actually a little denser, or a lot denser than the aluminum oxide when it's a liquid. So in videos you'll see online and in the practical uses on the railroad, they will have a big pot of this, melt it all at once, and then it will drip the iron out into whatever they want, whatever shape, mold they want to use, and then the aluminum slag either cools inside of the crucible or melts or just sits on top, and then they grind it away later. Pretty cool though. Thermite has a few industrial uses. It's often used while building or fixing a railroad to weld the two tracks together. They start by building a mold around two rails, and then they set a crucible on top and light the thermite mix. As the iron melts, it will flow out of the bottom of the crucible and into the mold. After some cleanup, they have two rails that have now become one. Another use is in demolition and situations where explosives would be too destructive or impractical. Thermite's often used to melt through various materials. It's often packed into a thermite charge that looks like this and set up around steel structures in order to melt through them and destroy whatever they're trying to take down. For example, the Reichstag building in Germany needed to have the dome rebuilt, but to destroy it, they couldn't use explosives, otherwise it would destroy the rest of the building. So they used a thermite charge instead to melt through the steel beams and collapse the dome to the inside. Overall, thermite is a very cool reaction that has a lot of practical uses and is very cool to do. Thank you to Dr. Breakall for helping me set up the experiment, and hope you have a good rest of your day.